Today I will be discussing AC power supplies and DC power supplies. An AC power supply, which I have right here, is called a Variac, and a Variac is short for variable alternating current. To give a short summary of what a Variac is, and I'll discuss more details about it later, a Variac changes one value of an alternating current voltage to another alternating current voltage value. That works by stepping up or stepping down the voltage inside the Variac. The input, which is pretty much the outlet voltage, is 120 AC volts. Demonstrate the Variac how it can switch from 0 to 140 AC volts. I'm going to go ahead and turn my multimeter on to the AC volt option. And I'll turn my Variac on. And starting from 0, I'll slowly turn the dial up and you can see the value of the multimeter changing. And yeah, as you can see for this Variac, it's able to change from 120 AC volts to an option that you can choose from 0 volts to 140 AC volts. And I'll talk more in detail on what a Variac does later on in the video. I will also introduce the DC power supply, which I have right here. It shows the voltage and amperage value that you are outputting from the hot lead or the red terminal and the black terminal or the ground lead. And it's an adjustable DC voltage supply. And just to test this real quick, I'm gonna hook these leads to a multimeter. And switching the multimeter to DC volts, I'm going to go ahead and demonstrate that this power supply that I have can go from 0 to 15 volts. A DC power supply works by converting the AC input from your outlet to DC. And that's done by first going through a full bridge rectifier, then a filtering capacitor, then finally you can use a potentiometer to adjust the resistance and thus adjusting the voltage of your output. Let's get into more detail on what a Variac does. A Variac has two copper coil windings. The one winding is called the primary winding and the other one is called the secondary winding. You can think of it like a transformer. This is what a transformer looks like. This would be the primary winding, this would be the secondary winding. The primary winding would convert 120 volts AC, and that would convert it to any value from 0 to 140 AC volts. Or at least that's the case for my Variac. And you can think of the 120 volts AC coming in from the red wire. As you can see here, it says 110, but the American standard is 120. So 120 AC volts coming from these two red wires. So here's 120 AC volts. And that's the primary coil. The secondary coil is where you can adjust your AC volts from 0 to 140 volts. Here it's fixed at 12 volts at the limit of 10 amps. But for a Variac, it has a dial, as you saw, that is adjustable. And the voltage is adjustable because there's a rotary brush that's on the secondary coil right here that moves according to the number of turns that you want on the coil. So the equation for this is you have the voltage of the primary coil over the voltage of the secondary coil, which equals the number of turns in the primary coil over the number of turns in the secondary coil. If we have the voltage of the primary coil being 120 and you want the secondary voltage or the voltage that you want to output, say you want it to be 70 volts AC. The number of turns in the primary coil is fixed, and let's say that's like 200 turns, say. And the number of turns in the secondary is X. And putting these two equations together, we have 120x is equal to 14,000 turns, and x is equal to around 117 turns. So this metal brush in the Variac would move up and down to make sure the exact number of turns would be around 117 turns. And the second equation that you have to keep in mind is that the voltage of the primary times the current of the primary is equal to the voltage of the secondary times the current of the secondary coil. All of this is possible because of Lenz's law, or the electromagnetic induction law. And how Lenz's law works is that you have the electric motive force, or you can think of the voltage of the secondary coil being equal in the change of the magnetic flux, which is represented by the derivative of phi b over the change in time. So you have two coils here. So let me draw my first coil and your secondary coil here. The current going through your primary coil, which can be clockwise on the primary coil, would lead to the electric motive force, or the current going on your secondary coil, going the other way. So here it would be counterclockwise. And the magnetic flux comes from this iron core. So back to a transformer here. This would be your iron core. So you can see here the iron core is just this outer layer here. And that's able to transfer the magnetic fields from the primary coil to the secondary coil, making the electromotive force, or the voltage in the secondary coil, possible. And to delve a little bit deeper, we have the magnetic flux being equal to the magnetic field strength times the surface area of the coil multiplied by cos theta, or the angle in which the magnetic field is pointing to relative to the normal angle of the coil. So say we have a coil again. Our magnetic field is going this way. So it goes here. Let me draw the magnetic field lines. And the normal to the coil is in a 90-degree angle, so it's pointing this way. And the magnetic field lines, as you can see here, is parallel to the normal. So cos theta would equal to 0. And that would be in its most efficient state. And you can measure the magnetic field strength, which is B, by using a Gauss meter or a Hall effect sensor. The area is just the surface area of the coil. So if you get a bird's eye view of the bottom part of the coil, it looks like a circle, and the area is just the area of the circle. And cos theta, as I explained here, in all transformer or Variac designs, it's going to be 0, or at least be close to 0. So cos 0 is just 1. So in theory, the magnetic flux should just be equal to the magnetic field strength times the area of your coil. Let's now talk about how a DC power supply works in a simple case. You would start off with the 120 volts AC from your outlet, and that would usually be converted to a smaller AC voltage value so that the whole circuit doesn't catch on fire. And we will be using this transformer and the circuit I made. Another thing that you want to make sure is that you don't want to exceed the voltage rating stated in the transformer for your primary or your secondary winding. So in theory, you can go from 12 volts primary AC to 120 AC volts on your secondary coil. But if you go too much, say like you feed it 180 volts, the transformer is going to generate heat and not actually convert the secondary voltage to a higher value. If you feed the primary coil too much voltage, then the transformer will catch on fire or even blow up. So I have my two leads here. You can think of these two wires as the two outlet holes that you see on your wall, and that would be connected to the red wires. Doesn't matter which way you connect it, it's AC, so the current will go back and forth. So there's this wire here and this wire here. So I have a multimeter here, and if we hook these two leads to the white wires, we should see the value on the screen being close to 12 volts AC. And these leads here just connect to my Variac that's outputting 120 AC volts. And then if I turn my Variac on now, it transforms 120 AC volts to close to 14 volts AC. And this value here is now more suitable for the circuit to not catch on fire or even blow up. And the AC volts that you are measuring, say this is your AC sine wave, like so. The AC voltage value that you set, say you set it on a Variac dial, or it's 120 volts AC set by the outlet, that's the AC voltage of the root mean squared. And what that means is you have your peak voltage, say it's like 170 volts peak, and you divide that by the square root of 2 to get your AC RMS, or to get your commonly known AC volt value. So if we take 170 divided by root 2, we get 120.2 volts AC root mean squared. And that's the value coming out of our outlet. The 170 volt peak is basically the amplitude of your sine wave. So say this is like the midpoint here. From this point to this point up here would equal 170 volts. And the value from this point to this point is also 170 volts. This time it's just negative 170 volts. So if I set my Variac to say like 80 volts, that would mean the AC volts based on the root mean squared of your peak voltage. And if we want to find the peak voltage, we just multiply your 80 volts by root 2 to get your sine wave amplitude of 113 volts. And that's your peak voltage. And don't worry, for your DC voltage, DC peak is just a flat line. You won't have to worry about that. And the RMS voltage for your DC line is just equal to the line itself. So if your DC power supply outputs 8 volts, say, your peak voltage is going to be equal to 8 volts. And your voltage RMS is also 8 volts. So you don't have to worry about anything regarding RMS or peak voltage. That's just for your AC component. Now, to convert your AC waveform to a straight DC line, you're going to need a full bridge rectifier or 4 diodes with a filtering capacitor. So I have this model here, and just taking a close look at it, one thing to note off the bat: to make your full bridge rectifier, your 4 diodes have to be parallel to each other on opposite sides. And that is indicated by the gray or white band on your diode. A diode only allows current to flow in one direction, from the positive side of the diode to the negative side of the diode. And the negative side of the diode is indicated by the gray or white band. And now you might be asking yourself, how do I know which of these 4 corners go into my alternating current source and which 2 corners output my DC line that I want? And to tell from that, I'm going to draw a few graphs on what you should be expecting. So I have my AC waveform, and say it looks like a sine wave just like this. Now, with a diode with current only allowed to flow in one direction, the bottom half of my sine wave gets cut out. So you can imagine that this part's gone and this part's gone. And my new resultant, or what I should expect, should look something like this. And this is my midline. And if I draw it, it should look like this. And this length here from this point to this point, we'll call this L, is equal to this length from here to here. So L for this length and L for this length, and they would equal to each other. And that's the graph that we should be expecting for our full bridge rectifier with our initial 4 diodes. And then we have the capacitors here, which are responsible for filtering out this top half into a linear DC output. And this linear DC output is equivalent to the AC peak. So the graph that we should be expecting would look like this. And how straight this line here is depends on how high your capacitance rating is. So if you have, like, say, a 2.2 microfarad capacitor, your DC line here might not be completely straight. It might look something like this, as I will show in this example here. It still has some ripple, but with a higher capacitance, all this will be straightened out to a more straight line. I will demonstrate capacitance filtering a little bit later into the video. One quick important note that I would like to mention is that if you have a 12-volt AC waveform and want to convert that to a DC waveform, from this method mentioned here, I would need to multiply this value by the square root of 2 to get my DC value. So this would be equal to 16.97 volts direct current. Now let's look at the diode configuration closely again. As I said before, the result that we should be expecting looks like a half wave. So this result here will determine what corner points I should be using to connect to my AC waveform. Some obvious notes is that 1/2 of the time taken is an active waveform. The other half is pretty much, you can just call it like a dead zone. It's not doing anything at all. And what that should tell you is that the diode is doing its job by not allowing any current through, thus not allowing any voltage through either. And we go back here, current and voltages flowing through by our AC waveform, not flowing through, and repeating back and forth. Looking closely here, take some time to think about it. Tell me which 2 points or which 2 corners on this model I made should be connected to our AC waveform. If you recall, is our transformer, which for reference, yeah, this is the transformer that we've been talking about. So now you've given it some thought. The answer is these 2 corners right here. This first half here would go through this diode right here, so positive to negative. The second half, it's not going to do anything because this diode does not allow the current to flow from this point to this point, and it repeats itself again. And this point here is the same case. Current flows from this point to this point, but not from this point to this point. Moving on, we need to determine which of these 2 points is for ground and which one is for hot in our DC line. We want our resultant to be our hot point. And looking at this closely, we can see the current is flowing through this way and this way, making this our resultant. So this is going to be our hot point. Our ground point is this point right here, and that's because this point will flow through back into our AC supply, which is our transformer. And to view these graphs more clearly, I have an oscilloscope right here that will show these graphs based on my diode configuration. So I have my function generator here. I set it up for 20 volts peak to peak. You can use the formula that I've discussed to find out what the common voltage AC value is. And here I also set the frequency for 10 Hertz. And to visualize this sine wave, this oscilloscope will show it by connecting my leads, which I have right here connected to my function generator. I have my oscilloscope lead, which my hot point is this point here, and my ground is this alligator clip here, that are connected to my function generator. Or you can think of it as a sine wave generator. And having the connection like so, this is my result. Don't worry about how to use an oscilloscope or how to use a function generator. I'll cover that in a future video. Frequency is 10 Hertz, as you can see here. My peak to peak is 20 volts, just like I set it up on my function generator. And yeah, this is my pure sine wave. Now for my AC source from my function generator here, I am going to connect that to my 2 points on my diode model. And these 2 points would be one here and one here. It doesn't matter where you connect them, you'll get the same result. And you can see that it's connected like so. This point here, as you can recall, is our ground. Taking a closer look at where the bands of our diodes are, this would be our hot point, this would be our ground point. And these 2 points here will display our resulting waveform. And this is what our resulting waveform looks like. And adjusting the time value for it, the result on our oscilloscope matches with the graph that I drew right here. Now, the capacitors, which are these little things on my diode circuit, will filter out this waveform so that the DC line will be at the peak of my AC waveform. So it'll be right here. And recall that I mentioned that the higher capacitance value that I have for my capacitor, the smoother my DC line will be. So I have 3 capacitors here, each with different values to test, so I can show you exactly what I mean. The first capacitor I'm going to be testing is a 0.047 microfarad capacitor. And the positive lead will be connected to my hot point of my diode circuit, which is right here. And the negative lead of my capacitor will be connected to my ground point of my diode circuit. And you can tell which is positive and which is negative on a capacitor by checking where the negative symbol on a capacitor is. So here is the negative lead here by this negative symbol. This capacitor, you can tell the negative symbol is here, negative symbol is here, and I soldered them all together on the ground point. So connecting this to my hot point now, this is what my graph looks like. And to get a better visualization, the DC line isn't completely smoothed out, but with an increased capacitance, you'll see the difference in results. And now, for a diode circuit here, moving on to a middle capacitor, and this capacitor has a value of 2.2 microfarads. You can see the improvement in the capacitor's filtering efficiency. And just to get a better view, it's not a completely straight line, but it's a lot better than our 0.7 microfarad capacitor. And finally, our last capacitor, right here, which has a value of 47 microfarads, we will get a completely straight line. You can see our straight line here. And disconnecting our hot point from our alligator clip, we are back to our half wave AC sine wave. And yeah, that's the first part of how to make a variable DC power supply like this one here. The next part that we'll be using is a potentiometer. And a potentiometer, which is also called a voltage divider, will adjust the resistance of one point to another. And that's basically this knob here that adjusts the voltage on my DC power supply. And this potentiometer here is rated for 1000 ohms. And you can also see that there are 3 pins in this potentiometer. And the equations that we can use for this potentiometer is the following. Is that the voltage of our adjusted voltage output is equal to our voltage input. Now you can think voltage input as the voltage AC peak that we've discussed earlier. And that's multiplied by resistance ratio of the potentiometer defined as R2 over R1 plus R2. And for the resistance value of our potentiometer, the max resistance of our potentiometer is equal to R1 plus R2. And for pins of our potentiometer, pin 1 is typically Vin, pin 2 is typically the voltage adjustment, and pin 3 is typically our ground. R1 is pins 1 to 2, and R2 is pins 2 to 3. And now to demonstrate the potentiometer, how it can change voltage, is that I have an LED attached to pin 1 and pin 2 of my potentiometer. So I have my potentiometer set up as you can see here. The red lead and the black lead connects to my power supply, and turning it on with a constant voltage, 4.6 is good enough. As you turn to your potentiometer left or right, you can see the resistance value and thus the voltage value adjusting. Finally, you might be wondering how we can convert a DC line to an AC waveform. And that's done something called an inverter. And you can buy these pretty much anywhere online. They're useful for converting battery power to AC power for everyday electrical use. And an inverter basically works by turning a switch on and off by using a component called a transistor, which the graph would look like a square wave. Then filtering the square wave, you can get a sine wave. I'll cover more about inverters in a future video. And yeah, that's it. I hope you found this information helpful. Thank you.